All right. Well, thank you all for being here. Our group is the Random Searchers, and we have prepared a data science project without strokes.
So to start off, a stroke is a medical emergency where blood flow to the brain is dangerously restricted, resulting in brain cell death. According to a 2018 study in the New England Journal of Medicine, 1 in 4 people over the age of 25 will have a stroke in their lifetime. If it's not treated properly, after effects can include restricted motion, paralysis, and difficulty communicating. The purpose of this project is to raise awareness of strokes and potential risk factors for strokes. This project uses a dataset from Kaggle, which contains features that can be used to predict strokes. Some features that we analyze include BMI, average glucose level, gender, whether someone's ever been married, and age. So why did we clean the data? The most important factor in data science is data. No matter what sophisticated machine learning models are used, the models are only as good as the data. Given a data set, there are usually false data points and missing data that could compromise the accuracy of our modeling, and cleaning data helps identify and remove errors. So the way we handled missing values, well, only BMI was missing any data, so we imputed this column by filling the missing values in with the mean of BMI. And for handling outliers, all of the numerical data in our dataset had some outliers, but we left them in because they were values that were improbable, but not impossible. Handling imbalanced data. Imbalanced data occurs when one of the target classes makes up a small proportion of the data, and our data is imbalanced because someone is much less likely to have a stroke than to not have a stroke, so we use SMOTE to balance our data. SMOTE balances data by synthesizing data with minority targets.
And now we have exploratory data analysis. As you can see above that our data was definitely imbalanced because it's unlikely for someone to have a stroke compared to not having one. And the target column is stroke with 0 representing no strokes and 1 representing strokes because we needed to put it in order for the computer to understand. As shown by the chart, the data is imbalanced with about 5% of the data consisting of samples with a stroke. Now is our pie chart. This one is on if someone was ever married and how that is in relation to strokes. It compares the proportion of strokes in people who have been married and people who have never been married. There's a slightly greater proportion of individuals with strokes for people that have been married. Our next pie chart is on stroke and gender. This pie chart compares the proportion of strokes based on being male or female. Most studies have found that females are more likely to have a stroke. However, this dataset sampled a population of people with a slightly greater proportion of males that had a stroke. It's a very slight difference, but it's interesting because either the people in our data sample tended to just have strokes either way and didn't reflect the majority population, or there could be, and generally it's just interesting things to think about in relation to previous research that has been done. And our next chart is on the proportion of stroke versus age. This chart demonstrates the relation between stroke and age. An increasing line shows a positive correlation between age and stroke likelihood. As you can see, there are a few outliers, such as at the age 0, babies can have strokes, for example. That was an example of an outlier that was definitely possible, but you can definitely see as well that your likelihood of having a stroke increases as you age. Average glucose level and age in relation to stroke is our next chart. This chart shows the relationship of those things. The blue dots represent an individual who has had a stroke. The region with the highest proportion of strokes occur at higher average glucose levels in old age. As you can see, the biggest concentration tends to be above 150 for their average glucose level, and age 60 and above, or perhaps age 50 and above for the highest level of people who have had strokes. The yellow dots are just people who have not had strokes, but the highest concentration of blue dots is in that region. Our final chart is our stroke data correlation heat map. As you can see, is a correlation heat map of a subset of features used in our data set. The subset of features shown include only features that have an absolute correlation of at least 0.08 with the stroke column. This figure is useful in feature selection for machine learning and useful for observing direct correlations between input features in the stroke column. This would be useful for feature selection if something was very, very closely coordinated, and we could just get rid of it because that would be redundant. And the one you see there is just like, you don't need to pay attention to that. But the what stuff that's most important in our research is the stroke column or stroke row. But for this example, let's just look at the stroke column. As you can see, there's a very high correlation between stroke and age, which would be interesting. However, that is not the only fascinating thing that we need to pay attention on to this, because there's other helpful information, such as possible correlation between age and hypertension. Stroke is simply just the stuff that we have our research focused on, as that is the target. And now to pass it on to the rest of the team.
Machine learning is a field of study that uses mathematical algorithms and data to make predictions and enhance the performance of tasks. Machine learning is considered to be a component of artificial intelligence. Machine learning models learn by using data to tune hyperparameters in the machine learning model. Machine learning is utilized in a wide range of applications, including speech recognition, email filtering, computer vision, and medicine. For our dataset, the target column strokes only has two classes, having a stroke and not having a stroke. Therefore, we explored machine learning algorithms for binary classification.
Logistic regression was the first binary classifier we used in our project. Logistic regression produces a probability which is compared to a threshold. If the probability is above the threshold, it is considered a positive case. The figure below is a confusion matrix which represents the predictions of our model. The value on the top left represents correct negative predictions our model made, and the volume on the bottom right represents correct positive predictions our model made. The other values represent incorrect predictions, and the top right is false positive and the bottom left is false negative. For our dataset, logistic regression had a low accuracy of 54%. However, the recall rate was high of a 98%. Recall is the number of true positives divided by the sum of true positives and false negatives.
The decision tree classifier was created around the 1960s. However, a similar concept has been used since the earliest written records. A decision tree classifier is a supervised machine learning algorithm that uses a tree-like structure to categorize outcomes based on the answers to a previous set of questions. In terms of accuracy, the decision tree classifier performed better than the logistic regression with an accuracy of 80%. However, the recall rate was low. Above is an example of a decision tree classifier, and below is the decision tree confusion matrix.
Multilayer perceptrons, or neural networks, are another machine learning algorithm that use connections, active functions, and layers to predict an output. Multilayer perceptrons can function as a nonlinear function approximator for either classification or regression. The study of neural networks is a subset of machine learning called deep learning. Deep learning can make predictions on advanced tasks like self-driving cars and conversational virtual robots like Siri. Regarding predictions on our stroke dataset, the multilayer perceptron model had the highest accuracy of 88%, but the lowest recall of 28%.
Machine learning results. The applicability of our models depend on the use case for stroke diagnosis. If one wants to use a model with very high accuracy, a null predictor, predicting everyone to not have a stroke, will be correct 96% of the time. However, if one wants to capture the population at high risk for a stroke, the logistic regression model performed best with a 0.98 recall in the has had a stroke category. On to our conclusion. From exploratory data analysis, we observed that the most impactful stroke factors were age, average glucose blood test. The percentage of individuals that have had a stroke increases after the age of 40. Additionally, individuals with higher average glucose levels and married individuals both have an increased risk of having a stroke. Regarding model predictions, it was difficult to improve accuracy past the null accuracy for this dataset. It was relatively small, just about 5,000 samples, with a highly imbalanced target distribution, which was about 5% minority class. Since models perform only as well as the quality of the data, the main improvement for future experiments in stroke prevention would be to increase the quantity and the diversity of the data.
Well, these are the members of our amazing team. Each member worked hard over the past few weeks to learn Python, data science, and web development. Thank you all for listening.